Okay, next we're gonna look at the theorems, Boolean theorems, which is kind of a law you can think of, but they are named as theorem only. So before that, I want to mention one thing, that is what is called literals or something. So this is basically the variable either in normal form or complement form. Okay, so the number of variable either in normal or complement form in each term of a Boolean expression. This is a Boolean expression, AB plus A bar C plus BC. This is each term, you can see, and inside each term the number of variables you will count 1 and 2 either in normal form or in complement form. That's what literal tells you. Number of variables either in normal or complement form in each term of a Boolean expression. Okay, so here if you will see, in each term you have, here you have 2 A and B, here also you have 2 A bar and C, here also you have 2 B and C. So how many total they are having? 2 plus 2 plus 2, 6. Okay, so one expression, 3 terms, these are 3 terms, and each term has 2 literals, A B, A bar C. I told you normal also works and complement also works. So 2 plus 2 plus 2 is 6 literals. So just remember this. Sometimes we don't call them variables, we call them literals. So you should be knowing that. Moving ahead, one example I have taken here. So just apply it. The binary operator not equal to. Okay, we are defining a binary operator not equal to is defined by the following truth table. This is the truth table in which they are defining this operator not equal to. So P, A and Q are the inputs, 0, 0, 0, 1, 1, 0, 1, 1. And P not equal to Q, they are defining it as 0, 1, 1, 0. Basically, it is looking like a XOR thing, no? XOR operator, right? Which one of the following is true about the binary operator not equal to? And since it's an XOR operator, so the options are given. You can see commutative but not associative, not commutative but associative, neither commutative nor associative. If you remember, NAND and NOR are the only ones which doesn't follow associative. Rest all of them follows associative and commutative both. Okay, so NAND and NOR are the only ones which follows commutative but not associative. So this, you can see, this is an XOR inequality detector. That's why it will be both. So TT looks like XOR gate, so commutative and associative both. So the answer will be A. Okay, so let me write it A. Okay, commutative and associative both are there. Now let's move on to the next theorem, which is or the next property or first theorem you can think of it is concessions theorem. Okay, this is sometimes called as redundancy theorem or sometimes also called as included factor theorem. Okay, what does it states is, if AB plus BC plus CA bar is given, you can write it as AB plus CA bar. Okay, so you can remove the redundant term, which is BC here. How you will get to know the redundant term? One term will be having a normal form, another term will be having complemented form. Which one it is? A is here. Okay, so here A is in normal form, here A is in complement form. So the remaining term, the third term will be having other literals can be removed. Okay, and that can be written as AB plus C A bar. Okay, you can prove it if you want. Not most of the time it is used, but you should be knowing it. Okay, so left hand side, if you will take, it is AB plus CA bar plus BC. I can write it as dot 1, right? BC dot 1 will be BC only, and law. So BC dot 1, and this A I'll replace it with A plus A bar. Okay, this is OR law, right? A plus A bar is 1 only, no? So we can replace like this, and now you can distribute it. So BCA plus BCA bar, this is CA bar, this is AB. Now you can take common. Which one you will take common? AB you can take common from this and this, and A bar C you can take common from this and this. So you will be having AB 1 plus C plus A bar C 1 plus C, and 1 plus C is basically absorption law, right? So AB it will become 1, this will become 1, so this will be AB plus C A bar, which is same as right hand side. Okay, so that is how you can prove it. So this is the consensus theorem, redundancy theorem. Redundant term, you are removing it. Okay, there are other forms of this consensus theorem. You can see that if you have this kind of thing, you have this, right? But let's say you have this kind of thing. Here you can see AB plus B bar C plus BC. Here B is normal form, this is complement form, so the remaining one will be removed. So the answer will be AB plus B bar C. This is another form of consensus theorem. Okay, not necessarily this one. Bar could be with C and B also, right? Similarly here also, if you will see A bar B bar, B bar C bar, and A bar C. Now which one is in normal and complement form? Here C you can see in normal form, here C you can see in complement form. So this guy will be redundant. So A bar B bar will be removed and the remaining term is as it is. Similarly, you can see here A bar B A B bar plus B bar C bar plus A bar C bar. Now here you can see A B bar plus A bar C bar. So how it is happening? You can see A and A bar is available in complement and normal form. So this will be redundant. So it is removed. Now there are dual versions of this as well. So these are dual versions. Duality we'll see. So dot has been changed to plus and plus has been changed to dot. Literals are as it is. That's how you create duality. So we'll see in the later videos. So here A plus B bar dot B plus C dot A plus C. Now here you can see B bar and B are normal and complement form. So those are the only one remaining here and this guy is removed. Okay, so A plus B bar, B plus C. Similarly, here you can see A bar and A are in normal form. So these two guys will be available here. This will be removed. Okay, so that's how you will look at the consensus theorem. A plus B, A bar plus C. Okay, not much of a use, but you should be knowing it. So this is the first theorem. The more useful guy is this one. Okay, so very important. You will be using it every time. Okay, De Morgan's theorem. There are two versions of this. So this is here first version and then there is a second version. Okay, so you can see that here first one is A plus B bar. If you have, you can write it as A bar dot B bar. Okay, left hand side if you will take, this is A plus B and then you take the bar of it, you will be getting A plus B bar. Okay, left hand side. And right hand side you will have A. Right hand side is here. And now this can be written as like this, right? NOR gate, right? Or then NOT gate is there, no? So you can combine it and you can use a single gate which is NOR gate. Similarly, right hand side if you will see A bar, B bar and it, so A bar dot B bar. And this you can use it like this. So A bar, B bar like this, no? So this is also a NOR gate, no? Bubbled AND gate is equal to NOR gate only, no? So this is the visual representation of this equation. Okay, truth table wise you can verify it. So A, B are the input 0, 0, 0, 1, 1, 0, 1, 1. A plus B if you will calculate, so 0, 1, 1, 1 and you take the bar of it, so 1, 0, 0, 0 it will become. Now you take A, B input 0, 0, 0, 1, 1, 0, 1, 1. Now calculate A bar. So it will be complement of this, so 1, 1, 0, 0. And B bar if you will take, it will be complement of this, so 1, 0, 1, 0. So if you will multiply these two, you will be getting 1, 0, 0, 0. Now you can see this and this guy are same. So that's how you can prove it via truth table. Okay, so this is the visual representation. This is the truth table proof of this, and it can be extended, applicable for more than one literal as well. Literal, I told you, it is the variable you can think of either in normal form or a complement form in each term of a expression. So here you can see you can increase the number of variables, plus C plus D plus E plus F like this, and it will convert into A bar dot B bar dot C bar dot D bar likewise. Similarly, you can have multiple variables in each term. So you can have something like AB plus CD plus EFG is here. Okay, plus dot dot like this. So it will become AB bar, CD bar, EFG bar. Okay, and if you will again apply De Morgan's, which you will be learning here, you will be getting A bar plus B bar, C bar plus D bar, E bar plus E bar, F bar plus G bar. Okay, multiplication of all. So this is another form. Okay, this is first form. This is another form which is A bar, A dot B bar is given to you. Then you can write it as A bar plus B bar. Here it is NOR version. Here it is NAND version. You can see that. right? So this is similar type. So left hand side, if you will see, and not gate is there. So and a dot b it will become, and here it is a b bar, right? So together you can call it as a NOT gate, a dot b bar. And similarly right hand side, if you will make a bar b bar plus, you will do a bar plus b bar. So this whole thing you can write it like this: bubble and bubble OR gate here, so which is a bubbled OR gate, and which is basically same as NAND gate. We have seen in the NAND gate previous section, right, how you can represent it with bubbled OR gate. So this is the visual representation of this equation. Now truth table wise also you can implement. A dot b is here 0 0 0 1 1 0 1 1. Now a b bar, if you will calculate, dot of this bar, dot of this bar, dot of this bar, dot of this bar. So 0 0 0 1. So it will become 1 1 1 0. So this is left hand side. You can also do right hand side. So right hand side is a bar plus b bar, right? So you can do 0 0 0 1 1 0 1 1. So a bar is 1 1 0 0, b bar is 1 0 1 0, right? From here you can add these two guys. So 1 1 1 0. So this is what you are getting. So you can see this side and this side, they both are same. Hence you can say this property holds. Okay, truth table version. Similarly, you can extend this guy as well, right? Application for more than one literal as well. Okay, applicable. So you can see a dot b dot c dot d dot e, if you do, it will become a bar plus b bar plus c bar plus d bar plus e bar likewise. Similarly, if you can have in each term, you can have multiple literals. So you can have a b c d e f g. So it will become a b bar plus c d bar plus e f g bar likewise. Similarly, you can have this version also. Means here it was dot. So if you will have plus here, so a plus b bar it will become, c plus d bar it will become, e plus f plus g bar it will become. You can see here, and in place of dot you have plus. Okay, and this is this if you will apply again De Morgan's the previous one, like how we applied here, no? So like if you will apply here the reverse, it will become a bar b bar plus c bar d bar plus e bar f bar g bar. Okay, so this is basically the De Morgan's theorem, the two types of De Morgan's theorem. Very very useful, always used in the minimization of expression. And this is the consensus theorem. Prior to that we have seen literals, and in the next video we'll be looking at some examples and also transposition theorem, okay, which is this guy.